Hey everybody, these are the class notes for section 8.1. So you should have most of this filled in. I'm just going to go in and throw in some highlights here and there. So first of all, diatomic molecule is the kind of focus of our warm-up. Diatomic, di means two atomic atoms. Okay, molecule means they're attached to each other with a covalent bond. So two atoms attached to each other with a covalent bond. That's as simple as it gets. It's in the definition there, or in the name, okay? But a molecule that contains two atoms, that is true, but we're going to mostly be talking about diatomic elements. So maybe you could add a little, if you can squeeze it in here, diatomic element would equal a pair of atoms, same element, okay? A pair of atoms in the same element. So the elements that exist this way, hopefully you already got these from the book. We had oxygen, nitrogen, hydrogen, and the halogens. If you notice, all of these end in GEN, oxygen, nitrogen, hydrogen, halogens. Now, the halogens themselves, if you look at their individual names, we've got fluorine, chlorine, bromine, iodine, and acetine. They all end in INE. Okay, so a memory trick for all of these would be all of the gens. Or if you want to be literal, because halogens is the name of a group, not the name of the individual elements, and the elements don't end in gen, okay, you could say all the gens and enes. Any element that ends with gen or ene on the periodic table is diatomic, meaning it exists in pairs. So for example, Br is never going to be bromine on its own. Let's see if I can remember how to do a subscript here. Nope. Bromine will be Br2. Okay, I figured it out. It's been a while since I've used Microsoft Word. Okay, iodine will be I2. Chlorine is Cl2. It's never going to just exist as single chlorine atoms, okay? Fluorine is F2. Then we have hydrogen, oxygen, nitrogen, same thing. Hydrogen is H2, oxygen is O2, and nitrogen is N2. Okay, so those elements exist as pairs. They'll never be single atoms in our chemical equations moving forward, okay? Now, when they are in a compound like NaCl, sodium chloride, table salt, okay, that chlorine doesn't have a 2 with it because it's one chlorine with one sodium attached to each other in that ratio in the crystal, okay? So it has to have a subscript in its pure form when it's an element, but when it's part of a compound, it does not always have that 2 because it depends on what it's bonded with. Okay, molecular compound. Definition is fine from the book. Compound composed of molecules. It's a covalent compound. They're sharing electrons, okay? Types of elements that form the molecular compounds. Non-metals. Non-metals. Metals want to get rid of electrons. They don't want to share to gain more. They just want to get rid of their extra electrons. They're going to form ionic compounds by giving electrons to non-metals. So metals and non-metals together make those ionic compounds. In order to have a molecular compound, you have two elements sharing. And in order to share, they both need more. And so that's going to only happen between non-metals. Okay, so non-metal compound or elements form molecular compounds. Okay, molecular formula, the existence. I just want to talk about this for a minute because in chapter 7, we talk about ionic compounds and how if you have an ionic formula like NaCl, it doesn't actually exist one sodium ion with one chloride ion bonded in nature. They don't actually exist that way. They exist in crystals that have billions and billions of ions in a 1-to-1 ratio, but it doesn't exist as a single little unit. But molecular formulas do, okay? These do exist. These do exist as individual units. These do exist as individual units. So if you see a formula like H2O, that's water, a water molecule can be an independent unit, and it is an independent unit as it floats around in our air and in rivers and etc. Okay, H2O, each one is its own unit and they can exist on their own. Okay, covalent formulas and ionic formulas. This is going to get just a little bit repetitive with what I've already said here. Okay, so covalent formulas, let's just start there. They show the actual number of atoms in a molecule and are not reduced to a lowest ratio. So remember back in chapter 7, ionic compounds, we always would reduce that ratio to the lowest possible ratio. Covalent formulas, we do not do that. We leave the exact number of atoms that are in the molecule in the formula. So for example, sucrose or glucose, C6H12O6. There are in a molecule of glucose 6 carbons, 12 hydrogens, and 6 oxygens. So we leave the formula written exactly that way. Even though all of those numbers are divisible by 6, we leave the formula written that way because a unit of glucose has literally that many atoms. But ionic formulas, just again, refresher from chapter 7, are always reduced to the lowest ratio of ions. Okay, because they don't exist as individual units. We simplify it, we put a ratio. Okay, if we had to put exactly how many ions there were, again, you're looking at a crystal with billions. You know, you don't have Na 1 billion, Cl 1 billion. You just write NaCl, write the ratio. Okay, so always reduce to the lowest ratio of ions in a crystal. Okay, so difference in what molecules and formula units represent. Again, we're just talking about that existence piece, okay? Molecules equal covalent compounds, first of all. Okay, covalent compounds. And they are individual units that exist independently. So molecules are covalent compounds. They are individual units that exist independently. Okay. Ionic formulas are called formula units. So formula units, by the way, the abbreviation for that is literally FU. So you can write FU on your papers in chemistry and not get in trouble as long as you're meeting formula units. So formula units are ionic compounds. And they show a ratio in a crystal, but do not exist alone. So NaCl, never find 1 sodium with 1 chloride. Okay, this bumped onto the next page because of my large typing over here, but still on the same page for your notes packet, properties of molecular compounds in relation to ionic compounds. So in the end of chapter 7, we talked about some properties of ionic compounds. And then in the end of, or in the first part of chapter 8 here, you have some properties of molecular compounds. So I'm gonna just type what you should have gotten from the book. So hopefully you already have this, but molecular compounds tend to have relatively lower melting and boiling points than ionic compounds. But that wasn't the only property that we talked about when we were looking at ionic compounds. We also talked about physical state and we talked about their conductivity. And so I want to add those two things. So in this box, I want you to add a couple more properties as they pertain to molecular compounds. So physical state can be solid, liquid, or gas. Okay, it depends on the compound. So depending on substance. And then the third property, again, that we really hammered home with ionic compounds was their conductivity. Okay, ionic compounds, when you dissolve them in water, they can carry an electrical charge because they're made out of charged ions, and they can carry that through the solution. That is electrical conductivity. Molecular compounds are made out of molecules that are little subunits. When we dissolve sugar, it doesn't break apart into atoms, it breaks apart into its subunits, each molecule floating around in the water by itself, okay? So when we do that, those molecules are not charged, which means they can't carry a charge through the solution. So they do not conduct electricity in pure form or when dissolved. Okay, so you could have put a period right here. They do not conduct electricity, but I just wanted to clarify. When they're pure or when they're dissolved, they're not conducting electricity, okay? Ionic compounds will conduct electricity when they're dissolved in water. Covalent compounds do not conduct electricity. So when we're afraid of, lightning hitting water, the water itself is not carrying the charge, but our water, pool water, river water, salt water, okay, it has lots of ions dissolved in it. And so that is what will carry the charge. Plus lightning is, enough energy to kind of make anything conduct. So we'll just, put that as an aside. Okay. All right. That is the end of the class notes for 8.1. And if you have any questions on the lesson check for 8.1, please talk to your teacher, but we will see you in class. Thanks for watching.